Excellent. All right. I shall introduce you, kind sir. Alrighty, everybody, thank you for coming this evening. We have a very distinguished speaker this evening. Let me admit people here. Uh, Alex is a developer advocate for Dremio, a developer and a seasoned instructor with a rich professional background, having worked with companies like GenEd Systems, Crossfield Digital, Campus Guard, and General Assembly. He is also the co-author of the O'Reilly book Apache Iceberg, the Definitive Guide. So please, if you would like, pick up a copy of that. And without further ado, I'll let Alex get into his presentation.
Hey everybody, I'm going to share my screen and here we go. And just to confirm, can you guys see my screen?
Yes, sir.
Awesome, so here we go. Hey everybody, my name is Alex Merced, developer advocate here at Dremio, and welcome to this presentation, the who, the what, and the why of data lake table formats. It's a very exciting topic that's very much at the center of conversations about data architecture in today's world, and I'm very excited to come talk to you about it today. But again, just to go a little bit more into sort of who I am, so most of this you've already just heard. Okay. Again, I'm a developer advocate at Dremio. I've worked in the web and data space for the last several years. I'm a co-author on the Apache Iceberg, the Definitive Guide book, which you can get yourself a free early release copy by scanning that QR code right there. And read the chapters that we have published already. We're constantly adding new chapters as we write it. It's been quite a journey writing it, and we're kind of like near the getting close to finishing up the last few chapters. So it's been pretty exciting to see this all sort of progress. I'm also a host of several podcasts. So we have Data Nation, which is sort of like my solo data podcast where I just talk about data stuff that just kind of is interesting to me. Select Star from Data Lake is a show that I do with my counterpart at Dremio, Dipankar Mazumdar, our other developer advocate. Gnarly Dataways is a show I host every week as part of being at Dremio, where we bring people from all across the industry to talk about really cool data lakehouse concepts and specifically. Just a lot of like talking about like also new features at Dremio and use cases and all sorts of good stuff. So all three of them are available on Spotify and iTunes. So if you guys enjoyed today's talk, make sure to subscribe so you can hear more. But with no further ado, let's move on to our featured presentation. So if we're talking about data lake table formats, let's kind of talk about sort of like what do they do? Because really what they do is they take that data lake and they turn it into a data lake house. So traditionally you would have a data lake. And essentially the way people would think about a data lake is just like a place where I put all the data. Okay, so basically if I'll extract all my data from my databases, get it from all like my IoT sensors, and just dump all that structured and unstructured data in this one place, mainly for a couple different reasons. One, because I could store structured and unstructured data on a data lake. And two, it was cheaper to store the data in the data lake relative to trying to store all of your data in the data warehouse, where the compute was more expensive, the storage is more expensive. I mean, again, cost looks different depending on sort of which picture you're talking about. If we're talking about like on-prem data warehouses, and then you're talking about like, hey, there's like the licensing cost for the software, the cost of the physical machines, and the cost of the staff to maintain that network, and all those costs. And the same thing with like an on-prem data lake house. You probably wouldn't have to spend as much money on licensing because you'd be using like open source software like Hadoop, but you're still paying for like, hey, these machines that oftentimes are maybe a little cheaper because you're not buying as powerful machines, mainly buying really spaces with like just large machines with large hard drives, and paying for the staff to kind of maintain that cluster. And then everything kind of moved to the cloud, and basically you have cloud data warehouses. So now, and then cloud data lakes, and now the costs are more about sort of consumption. So like you're talking about your costs as sort of what is the cost of that compute, what is the cost of my storage consumption, what is the egress fees, and so forth, and just normal sort of API object store access fees and things like that. So even then, when you use a data warehouse, oftentimes there's like a markup on that. So a markup on the storage, a markup on the compute, and all that stuff. So again, still cheaper to kind of put your data in the data lake. But the other problem was like, hey, in the data warehouse, generally your data is available to all the tools that are kind of built into that particular data warehouse platform. And that's fine and good and satisfies plenty of use cases, and oftentimes have a nice, easy interface, and it's kind of in a nice bow package. But what if you need other tools, especially in today's world where you have sort of the growth of data is leading to a problem where the use cases for that data and the ways we use data are expanding faster than any platform can add features. So in that case, you can either just say, hey, I'm not going to explore those use cases, or two, you can say, hey, I'm going to have to expose my data to more tools. And making multiple copies of the data into different platforms gets really expensive really quick. So how can I facilitate using more tools without, really compounding my costs? And this is where table formats kind of fit in. By having a table format and data catalog on your data lake, basically the table format unlocks all these abilities that your data lake didn't have before: asset transactions, time travel, all these things that normally you'd expect in a data warehouse, but not necessarily as functionality in your data lake. So basically, it turns your data lake into a database, but not just a database for a particular platform. It's essentially a database that other tools can then just plug into and run operations on your data, giving you access to whatever tool best satisfies the use case that you have. So making basically the data lake the center of your data world, making it into a data warehouse, thus the term the data lakehouse. So again, the piece that really kind of converts A to B is really a table format. Okay, the difference between having a sea of Parquet files versus having that metadata above those Parquet files that allows your favorite query tool or data tools to be able to actually look at your data as tables instead of a sea of files. Um, yeah, so that's essentially sort of like the why this matters and sort of like how it's transforming the way we architect our data. Now there are multiple table formats out there, sort of competing to be sort of the center of your data lake world. Because if they are the center of your data lake house, that's good for them. Every technology wants to have market share because it's going to fuel development of that project and just make it a more robust project. So Apache Iceberg is the first one we're going to talk about, which came out of Netflix. And so basically, what happened is that Netflix was having this challenge. So basically, the challenge was, well, they were using Hive. Okay, so you had before when you were just talking about pre data lake house, data lake world, you would kind of use your Hive format. And again, Hive existed because when Hadoop first got created, you would use this thing called MapReduce to run analytics on your Hadoop cluster. But it was really tricky to write all these like all this Java code to do this stuff. It was really tedious. So the idea was like, why can't I would rather write SQL? And what Hive does is just takes an SQL statement and then converts it into that MapReduce job. Or at least that was sort of its original impetus. But in order to be able to write SQL, you need to know what a table is. Okay, so what happened is that Hive said, okay, we have to figure out how we're going to know what a table is. So they came up with the structure of saying, hey, a folder is a table. And this allowed it to work, but it had all sorts of problems with it as far as like you couldn't really do really granular updates in a very efficient way, because essentially since you're tracking things by folders and subfolders, aka partitions, the basically the unit, the most fine-grained unit you could do sort of like atomic operations was really like a single partition. Even if you wanted to update multiple partitions, you weren't really able to do that in a good, consistent way. So there was a lot of imperfections, and again, having to depend on the file system, you're doing all these file listing operations that were really slow. So Netflix was like, this is not working for us, we needed another solution. So basically they designed this, okay, which is there. So they moved away from looking at your table as a folder with subfolders, instead of just saying, okay, we're going to have metadata that actually lists out the individual files within the metadata. Okay, and basically those list of files are called manifests. Okay, but ideally we're going to want to have those manifests kind of grouped by partition. So like generally all the data files, all the Parquet files that we list in this manifest should generally belong in the same partition, depending on how you set up your table. And basically at different points in time, your table will be your table is made up of multiple different manifests. So we need to kind of track which manifests belong to your table at this particular point in time, and these become a snapshot, aka a manifest list file. Now we need to track, so basically this file tracks, hey, which manifests are part of the table, but there's going to be multiple manifests because you're going to have multiple snapshots. Every time you change a table, you create a new snapshot. So we need some file that tells you, hey, what is the current snapshot? What are the previous snapshots in case we want to query the previous snapshots? What is the schema of the table? What is the partitioning schema of the table? And that's this metadata file. Okay, so between these three categories of metadata, the listing of the individual data files, the listing of the groups of data files, and just sort of the overall table structure, by having these three types of files, an engine can plan a much smarter query without having to do all these file operations. And the way an engine could discover that this table exists is through a catalog mechanism. And basically, what the catalog's job is done, which there are several different choices of what you could use for a catalog nowadays. That could be a whole other presentation. Basically, just tells the engine, like a Dremio or a Trino, that hey, for this particular table, this is the metadata file. And then every time there's a new transaction, we write some new data files. We'll write some new manifest to list those data files, create a new snapshot, and then create a new metadata file, and then swap out that reference in the catalog. And that swapping out of the reference in catalog allowed there to be ACID transactions. Because you're tracking these multiple snapshots, you could do time travel. Because you're not doing all these like file listing operations, you could literally just update a single file. So if you wanted to do granular updates, just like, hey, I wanted to update these like 2 rows, they're not going to be really massive partition-wide updating operations. So overall, it just made a lot of those problems that Netflix was having much easier. And the beauty of the Apache Iceberg project is that they really kind of try to keep the scope of the project simple. So it's really just a spec in the sense that it's a standard of how you write this metadata and how you read this metadata that tools can follow. And any tool that decides to follow that spec and implement that usage can then read this format. There's no extra tools that are needed to work with it. So in that case, everything is part of like this standard, and then other tools can then build on top of that standard. Then there's Apache Hudi. Now Apache Hudi came out of Uber. Okay, so Uber does a lot of streaming of data, right? Because you're having all these people who are real time getting cars and getting a ride from point A to point B, and Uber needs to be collecting that data, processing that data pretty much as in real time as possible. So Apache Hudi's architecture was really geared towards the streaming use case. Like that really was sort of like, hey, this was designed for that. And the way it works is that as transactions happen, okay, there are commits. Okay, so at the end of the day, all three formats have this concept of like a commit, a snapshot, a change in the table. But essentially what Hudi's doing is that every time there's a change, it falls into different sort of categories. So you can see here, like there's commits, there's changes to the table, and each of them are timestamps. So basically what it does, it constructs a timeline. So in that case, when you refer to the table, you don't say, hey, I want to query this particular snapshot. You can just say, hey, I want to query the table as this time. It can then, based on these commits and that timeline, and say, oh, it can determine which events are relevant and then reconstruct the table based on those series of events. And, you might have rollback transactions, compaction transactions, but basically everything kind of gets tracked. Every type of transaction gets categorized and put into a timeline, allowing you to do that. Another aspect of the Apache Hudi project is that it's not just a spec. It's not like just a way of writing metadata. It's actually also a service. So this makes it a little bit different than some of the others, that there's this tool called the Delta Streamer tool that runs alongside. So essentially to use Apache Hudi, it's not only, hey, I'm going to write my metadata this particular way, you're also running this thing called the Delta Streamer that basically in parallel is doing things like compaction and optimizing the data files. Because the idea being is that, hey, you want to optimize as the data comes in, because again, the idea is that the data is just kind of coming in constantly, so you want to optimize in parallel. So basically, you have this service that you would have to deploy and manage. So there's a little bit more overhead in getting set up with Hudi because you're deploying. You also have to sort of maintain that Delta Streamer service. It's just not the standard of how you write the metadata, but that gives you a little bit more clarity on the scope of the project. And I think when you take a look at like comparisons between the three formats, knowing sort of the differences between like whether like services are part of the project or not is important in deciding when like people compare features, because oftentimes they'll say, oh, well, this feature doesn't exist, but it's really the difference is that project doesn't build out services versus does it build out services. And oftentimes, even if the project itself doesn't build out a particular service, that service is available elsewhere. And I'll come back to that after we go over Delta Lake, which is our next one. So Delta Lake came out of Databricks. So basically, Databricks is trying to create a platform that allows people who work with data lakes more in depth, particularly initially using Spark, nowadays using like their newer engine, Photon. But the idea was, well, if we're going to make this more snappy on the data lake, there needs to be some sort of like layer that's going to allow Spark to be able to do operations more efficiently. Okay, and be able to understand, hey, what is this table? What is this data set more quickly? So they created Delta Lake. And Delta Lake works very much sort of like the way Git works. Okay, so if you're familiar with like Git for like software development, every Git commit is basically a delta of lines of code. So basically, every time a line of code changes, it's treated as if like this line was removed and this line was added to that particular spot in the file. And based on those changes, those commits that track changes among a group of files, you can then reconstruct the state of those files. So, but in the world of data lakes, the actual data files in all three of these formats, the assumption is that the data files are immutable. So you're not updating those same Parquet files. What you're doing is that every time you make a change, you're creating new Parquet files. So if I update a record, then that whole Parquet file gets rewritten. And then now that new Parquet file becomes part of that state of the table. That's true for all three of these. So essentially what happens, each delta log basically instead tracks the changes of which files are part of the table. So like each delta log, aka commit, will say, okay, well, these files were added, these files were removed, these files were added. But then what happens, you get so many commits you can get some latency. So to help kind of address that, they created like this checkpoint mechanism where periodically you create checkpoints that summarize a group of commits. So that way, every time you're reconstructing the table, you can not have to read each of these delta log files. You can skip it because you have a checkpoint that summarizes it. And you can then just go, okay, read the checkpoint here, and then go back to determining what files are part of the table based on these delta logs. Okay. And so going back to that whole idea of like optimization and services, at the end of the day, like all three formats for the most part, I would say are a year ago where the story would have been different, but now I would say like feature wise, they pretty much all have the same capabilities. Sometimes they have little different takes on some of those capabilities, but for the most part, all the features you'd expect, things like ACID transactions, the ability to time travel and run queries on the state of the table in the past, being able to evolve the schema and change columns, rename columns. All these things are in all three formats. Okay, and how about the ability to optimize? Well, while Hudi has a built-in service as part of the Hudi project that you can run that does optimization services, Iceberg and Delta do have places where you can do services. They're just generally external to the project. So Delta Lake, a lot of what makes it more feasible to use Delta Lake is actually built into the Databricks platform. So a lot of the things to like automate optimization of your Delta Lake tables is built into Databricks. A lot like the new feature with like Uniformat, and I'll bring this up again later, that allows you to kind of write Iceberg metadata along with your Delta Lake tables. That requires you to use the Unity catalog, which is part of the Databricks platform. So a lot of those services are not part of the Delta Lake project directly, but they're built into the Databricks platform. Iceberg, you have multiple parties who kind of provide those services. So when it comes to like optimization, you have like Dremio with Dremio Arctic, which is a catalog that provides catalog level versioning and table optimization and management. And then you also have Tabular, that also provides a catalog that provides automated optimization of your tables. So the idea is like those services exist. They're just external to the project itself. So again, if you were to factor in that, they're basically you have pretty close to feature parity on all three of these formats. It's just a question of sort of like which features may tie you to a particular vendor at some point. So ACID transactions. All three formats have ACID transactions. So I mean, basically, you're going to have atomicity, consistency, isolation, durability. Because basically what's going to happen is that they all use snapshot isolation. How they capture those snapshots is different. So again, Iceberg has that sort of metadata tree structure. Hudi captures it in that sort of timeline. And then Delta Lake is through those delta logs that just capture the diffs between each change in the table. So you're going to get that benefit regardless of which format. Again, slight differences in how that's done, but for the most part, like, you have it on all three. A schema evolution, the ability to like change, add new columns, remove columns, rename a column, change data types, reorder fields. That's going to exist in all three formats, so they are all pretty much at parity there as well. Okay, now again, one thing to always keep in mind with all three formats, any tool that works with data, just because the format exists and they build support for the format, doesn't necessarily mean you get all the features overnight. Okay, so while all the features may be available in the format because they've standardized how those features would exist, each tool still has to build their support for like a lot of these features. So one thing to always be careful for is just because X supports whatever format, don't assume that you get all the things with that particular tool. You want to always look into like, hey, what is the level of support they have for that format? Like, can I write to that table with that tool? Can I read those tables with that tool? If I can I update, like, can I create tables? If I can I update those table schemas with that particular tool? So there's what the format supports, and there's what the tool you're using with the format supports, which is, again, not to discourage embracing this. It's just more like these are the questions you want to ask, because last thing you want to do is like you build out this whole setup and then you didn't ask those questions, and there's a piece missing that you could have avoided had you were thinking about those questions. Um, cool. Okay, fish and row level update. So this is the conversation between cow and more. So basically, copy on write, merge on read. So let's first talk about high level, what this is referring to. All three formats by default are generally going to be copy on write. So copy on write just means that, let's say I were to update a single row that belongs in Parquet file 1. Okay, the way the format's going to handle it is that it's just going to rewrite that file. So if that file has 1,000 records and I'm only updating one, I'm rewriting that file and I'm rewriting all 1,000 records. And, that's fine if you're not doing frequent small updates and deletes. Like if you're not often the times updating a few rows or deleting a few rows, then that's fine. It's going to be better off on the read side, because then on the read, they're not having to reconcile any changes. They're just reading the data files as is, and that's all fun and good. But again, you get that cost on the right side because you're rewriting that entire file that you've updated, even though you only updated a little piece of it. So what happened is that Hudi was the first one to have a merge on read setting. So the way Hudi implemented this is that it's a table level setting. So a table is either a copy on write table and does copy on write for updates, or it does merge on read. And generally the way merge on read works is that instead of rewriting the entire 1,000 records, is just going to write, like, let's say you update one row. It'll write a new file with that one row, and then somehow it's going to track that record has been deleted it should be ignored in the old file. Okay, so a merge on read table in Hudi would handle writes that way. So basically, if you're doing frequent updates and deletes, you basically don't have that cost on the right side because you're not rewriting the entire data file. But theoretically, there's a cost on the read side, because what happens at the read then has to reconcile those, that, hey, they have to be told, hey, ignore this row, and that all takes operational time. That's generally why you want to run what's called compaction, to sort of reconcile those files and rewrite those files in parallel. And in Hudi, the Delta streamer kind of handles that. So basically, you'd be writing merge on read, and at the same time, the Delta streamer parallel is kind of rewriting those files to avoid some of that hit to the read side. In Apache Iceberg, it uses a concept of delete files. Okay, so essentially what would happen is that it writes a file that captures either which row in a particular file was deleted, which is referred to as a position delete, so it's the position of the file that was deleted, or it's called an equality delete, which captures sort of the values of the columns that was deleted. And each of them have different sort of write and read trade-offs. But again, you would run compaction to sort of in parallel, or through a service like the services I mentioned earlier, as Dremio, Arctic, and Tabular, or come up with your own service that kind of runs compaction in parallel, so that way you minimize that hit to your read. There's different ways of doing that. We do get a lot more detail in that. I have some blogs that cover it, but we do get really in detail in that in the book, and I think that chapter might be in the early release at the moment. And then in Delta, basically they were the last ones to implement this feature. It's a new feature called deletion vectors. And always the thing with like Delta Lake, you want to make sure when you research like the features is like the thing like are they available all around? Because there's like really like two versions of Delta Lake. There's like features that Delta Lake has when you use it on the Databricks platform, and then there's features that are available even if you're not using the Databricks platform. So always read the docs carefully because it can sometimes be a little confusing on when you have a feature available to you in either situation. Um, you'll see if you read the docs. It's sometimes tricky to kind of parse that out. But basically, they have a feature called deletion vectors that tracks those the differences. So essentially, a deletion vector is the same thing as like a delete file, where it's saying, okay, hey, these are the files, these are the records that were deleted. Don't rewrite the whole file, but we'll keep track of those deltas there, so you don't have to rewrite the whole file. Cool. All three of them now have Z order. So Z order is just a way of sorting your files. So when you're doing compaction operations, and again, compaction just means taking, generally the idea is taking all your smaller files and trying to rewrite them so they become fewer larger files. But all of them have compaction capabilities, but now they can also allow you to sort your data as well. Okay, so in Hudi, again, the Delta streamer tool is oftentimes doing all these things in parallel. So how you sort it, all this kind of stuff. Apache Iceberg has generally a lot of these operations built into the libraries, and again, you could use those operations in the libraries to create your own service, or you can use some of these existing services like Dremio, Arctic, and Tabular. But Z-order, what it does is that allows you to take basically sort your data equal weighted by multiple fields. One of the best visualizations I've ever read to explain like Z-order is thinking of like they say like you're trying to find where something in your bedroom is. Okay, so what you do, you could search all of your bedroom, and that would take a really long time. Okay, but if I could basically, if I knew that like the thing that I'm looking for is somewhere, let's say approximately at the location of 75x 25y, well, I can then determine that, hey, this is not where I'm going to look, this is not where I'm going to look, and this is not where I'm going to look. So I've just eliminated the surface area of where I have to search by 75%. So Z-order kind of does this, but through sorting. So the idea is that what you do is instead of sorting by one field and then sorting by another, you say, okay, all the data that is X has a value of X 0 through 50 or Y 0 through 50 will go into this bucket. And then we create the 4 buckets, and then we write the files. So basically all the data that has these two values in these ranges are going to be in those data files. And if I'm oftentimes querying based on those two fields, what's going to happen is I'm going to be able to quickly sort of like, again, eliminate like 75% of that surface area of what I'm searching. So, and then that's the whole bottom line with all these formats. The idea is if they can provide you ways to eliminate the number of data files you have to read, you're going to get faster queries. Okay. So, quick little side note, all three formats have different approaches to what's called data skipping. The idea of being able to determine, hey, I have 1,000 Parquet files in this data set, in this table. But do you need to scan the 1,000 Parquet files? No. Ideally, you scan as little as possible. And traditionally, that's the role of partitioning. You would partition data, and ideas if you took advantage of that partition column, you would scan less data. And all three of them do use partitioning in different ways. But even beyond that, they generally keep track of statistics for the different fields, so that way you can even do further pruning. So Apache Iceberg captures different statistics at the partition and individual file level that allows you to do much more fine-grained pruning, especially if the data is well sorted. Hudi maintains a metadata table that has different stats for the different columns that serves the same purpose. And then Delta Lake, I think, they coincide in those Delta log files. They have metadata on the columns as well that can be used for data skipping and helping like say, hey, I don't need to scan these data files. So all three of them have mechanisms, places where they store this kind of metadata for engines to be able to create really nice, crisp query plans. Okay. Lakehouse versioning. Okay. I recently did a whole presentation on this topic. This is an exciting topic. So the idea here is versioning is a if you really want to kind of have like full on data lakehouse, one of the things you could do in a data warehouse is you could do rollbacks. Okay, like generally if you make some mistakes, you could roll back to a previous state of your warehouse. You could create experimental environments. You could create you could isolate ingestion. These are things you generally can do on many different warehouse platforms, multi-table transactions, things like that, that generally aren't available on the lakehouse. But with some sort of versioning paradigm, you can. Okay, so generally, basically that's going to be the benefit of like versioning. Now, if we take a look at Hudi and Delta Lake, right now the only versioning solution that they have that's is LakeFS. Okay, so that's file level versioning. So what LakeFS does is that it tracks the files in your S3 or S3 compliant storage through the URL. So essentially, like you'll see, like your S3 URL would have like a different word in it depending on what branch it is, and that's how it's able to understand sort of like, oh, okay, this is data. We're looking at this branch or that branch, which is fine, and that works fine for Delta Lake and Hudi. Okay, now Apache Iceberg works a little bit differently because again, you're not just it doesn't rely on the folder structure. It doesn't rely on the file system. It relies much more heavily on the metadata and the structure of the metadata. And right now, that metadata generally holds absolute file positions. Okay, so basically, it doesn't use relative file names. So in that case, you can't really have different file paths with different branch names. So that kind of created an issue with using LakeFS for Iceberg. So what LakeFS did is they created their own catalog. So you can use Iceberg with LakeFS for file versioning, but you would have to use a LakeFS catalog. The one issue with catalogs in Iceberg is that each catalog is a way for your tools to discover what Iceberg tables you have. But if the tool that you're using doesn't support the catalog you're using, then it can't discover your Iceberg table. So that's another question. If you're using Iceberg, the question you always want to ask is what catalog mechanism am I using, and do the tools I want to use support those mechanisms? Okay, table versioning. Okay, and LakeFS is probably like the newest catalog in Iceberg. So I don't outside of like Spark and Flink, I'm not aware of any other support for that catalog yet. Again, it always expands over time, but at the current state of things. Table versioning. Iceberg is the only one that natively has versioning built into it. Okay, so all three have like at least a snapshot isolation, so you can always like roll back, the table. You can query different versions of the table for sure. But as far as like creating branching and having sort of branching chains of changes, Iceberg is the only one that allows you to do that at the table level through the metadata. So basically, you can actually have different chains of changes to the table that exists in the Iceberg metadata. And this also allows you to tag different states of the table, so that way you can easily replicate certain states of the table. But it only is one table at a time, so it doesn't facilitate multi-table transactions, because basically branching for one table doesn't necessarily coincide with the branching for another table. So in that case, if I were to make changes to two tables, I'd have to commit first to table A and then commit to table B. And I'll come back to executing multi-table transactions in a second. But Iceberg also, another really favorite project of mine, is a project called Nessie. It's another open source project which provides a data catalog for Iceberg. It could be a data catalog for anything. It's just primarily right now used for Iceberg. That captures versioning at the catalog level. Now, the beauty of Nessie is that it's just capturing basically all it's really tracking is a bunch of namespaces and metadata related to those namespaces. So essentially, every time you register a table, it's just registering a namespace or a key to that table with a little batch of metadata. And for Iceberg tables, that metadata is really just consists of one primary thing, which is the location of the metadata, because that's what catalogs do. And so that's really lightweight versioning. You're not having to capture differences between all the different files in the table, just where that metadata file is. And basically, when it's capturing that snapshot, it's doing it for every key or every table in the catalog. So in that case, I capture not versioning of one table, but of all the tables. So I can create a branch to isolate ETL, and I'm creating a branch for all my tables in my catalog. and then I can do transactions across all those tables, and then merge or publish them simultaneously. So I can do multi table transactions, which you can do with LakeFS. Like LakeFS, you can make changes because again, it's just capturing the files. So if you change the files from multiple tables on a branch, you can then publish them through a merge. The difference is that Nessie actually recognizes like the concept of table, so saying, hey, this namespace belongs to this metadata file. Other cool things about like Arctic is that you can roll back all your tables. Again, you can because you're rolling back the catalog. You can tag the catalog commit. So this means that hey, let's say someone wants to do some experimentation on the data. What happens usually? You create a whole never environment, and you create a whole copy of the data, so that way they can experiment with the data. But you don't have to. You can create a branch that's just for experimental purposes of the whole catalog, and now they can play with any table they want and make changes and add things and do whatnot, and it's not affecting the mainline versioning of all those tables, nor are you duplicating your data storage because you're not making an extra copy of the data. Again, all three of you kind of offer that ability to create zero copy clones through branching to some level, but Nessie again is just a little lightweight. It's a little lightweight in what it's tracking, which allows you to do that sort of zero copy branching in a very nice way. I think in the future it may be able to track Delta Lake. Like the functionality is built in there. It's just more waiting for a pull requests from the Delta Lake project, which has been sitting there for a year. They just won't merge it. But Nessie handles Iceberg beautifully. I have some great tutorials where I show how that works, and it's the backbone of that Dremio Arctic project. So basically, you could deploy your own Nessie server, or you could get the Dremio Arctic, which also gives you the automated table optimization along with it. Plus a really sweet UI. I made a post on LinkedIn about it earlier today. But yeah, those are your options when it comes to versioning. So in Iceberg, you have lots of options. Generally, with right now with Hudi and Delta's, LakeFS is your main option. LakeFS works primarily with S3 and S3 storage. So if you're like using like Hadoop on-prem storage or using non-S3 compliant storage, then you can't use LakeFS. Yeah, and as I currently understand it. Cool. Partitioning. So again, partitioning is something that all three formats have. Okay, so Iceberg, you have two really cool features in partition evolution. This is one of the few times where like they don't all have the same feature. Iceberg is the only one that has partition evolution. You can actually change how you partition the table. So let's say you've been partitioning the table by year for like the last couple of years because you're only getting so much data coming in. But now let's say you're talking about sales data, and the sales data is coming in, you're getting a lot more sales. The girth of the data requires more fine-grained partitioning. So you shift over to month, and maybe eventually to day. You can do that without rewriting the whole table, okay? Because you can actually change the way the table is partitioned without having to rewrite everything, which is pretty awesome. What will happen is that the old data that was partitioned by year will just stay in a year basis, and then all the new data will come in and be partitioned by month. And then basically when the engine's planning the query, all that data is in the basically which partitioning scheme was used is all tracked in the metadata, so it can properly plan regardless what portion of the data was created in what format. And you get the benefit of both. And then later on, if you do want it all to be, you can rewrite it on your own time if you want. Then there's hidden partitioning. So one of the pain points with like Hive in the past, it was partitioning. You could do partitioning in Hive, but let's say you want to partition by year. Let's say you had like a date column or a timestamp column. You would have to create like a derived column, let's say like a month field, and then partition based on that field. Now your normal data consumer is not going to be thinking, oh, I should query for all data, for all sales between this timestamp and this timestamp, and then also say, hey, between this month and that month, because you think the timestamp would cover that already. But because of the nature of partitioning in that way, you had to do that, because if you partition based on the timestamp, it would create a unique partition for pretty much every millisecond. So you had this sort of cumbersome, like you kind of had to know that these extra columns existed and that you had to filter by those columns to make sure you actually got the benefits of partitioning. The way Iceberg tracks partitioning is that it tracks it as, if I were to do like a yearly partitioning, I don't have to create a year field. What it does is I can they have these special like partition transforms that says I'm partitioning the table based on the timestamp field, but not specifically on its raw value, but its transformed value. And then it tracks those transformed values in the metadata so it can do the planning from the metadata. But your actual data files only have a date column or a timestamp column. You don't have this extra column, okay, you have to worry about. And basically, you don't have to add those extra predicates. So it makes it where someone who's just querying the table and doesn't know how this table was engineered, they don't have to think about it, and they're going to get the benefits of the partitioning if they hit that, if they're filter on that timestamp column. Now, Delta Lake kind of gets to the same place, but in a slightly different way. They use a feature called generated columns. So what this does is that you still do need to have the extra column. So your Parquet files will have an extra column, but the idea is that you can set a rule that whatever tool is writing can know, oh, you set a rule that's saying, hey, anytime I write to this column, do this, apply this function, and the result of that will be in this other column. So that way you don't have to come out kind of create those values on your own. And if a query comes in on, let's say, the date column, it knows that if you partition based on the generated column, it'll know to basically add the additional predicate based on your query. So in that case, you kind of get to the same place. You still have the storage penalty there, but there's other use cases for generated columns other than just the partitioning story. And then Hudi doesn't have a feature like this in general, but basically it's like they rely on that column stats index that they have in the metadata table to kind of handle a lot of that data, those data skipping needs. So basically, they're like, okay, well, the metadata table is going to have these stats on those fields, and based on your query, it should be able to prune the files regardless of the partitioning scheme. So again, you end up kind of getting there, but again, different queries are going to perform slightly different ways and depending on format. There's no perfect way of doing this. So that's why at the end of the day, like, and this, well, I might as well address it now. Like when you hear people talk about benchmarking, like everyone always benchmarks like the TPCDS data set. And what happens, like a lot of times people create tools that are sort of optimized for TPCDS, but then that might not necessarily be relevant to like your particular query patterns and your particular sort of data usage and data shapes. So bottom line, if you want to know which one's going to be the fastest, not just, and again, the format is just a way of reading the metadata. What's like, you can take the same format, use two different tools, two different query engines, and get completely different performance. Because again, each engine has to create their functionality with that format. So if you want to know what's going to perform best with you, you want to test the formats with the tools that you use. Okay, so basically, if you use Flink on a daily basis, Spark benchmarks of these formats aren't going to mean much to you. So just like a side note, when you're evaluating these things for actual like decision making, you do want to take that step where you run workloads that you actually run on a daily basis against these formats to see like what would this actually look with your type of workloads. Now, format interop, this is a new sort of like space, which is really interesting. Like, because the question is, at the end of the day, like, more than likely, we're going to live in a multi-table format world. Okay, like, there are different times, there are going to be different use cases. Like like my opinion is, I think like Apache Iceberg tends to be sort of the best like general use case one. So like where would I put like the majority of my data gravity? Probably Apache Iceberg. But if you're using Databricks, there's gonna be a lot of benefits to using Delta Lake, okay? Because there's a lot, they provide you a lot of extra stuff when you're using the Delta Lake format, so it would make sense to use it. And if you're doing like streaming, Hudi is really well designed for that particular use case. And you might decide to basically use like OneHouse, which is a vendor that provides a lot of services for streaming into Hudi. You might use them to kind of help stream in the data, but you don't necessarily want to have may not want to have all your data in Hudi. So you still maybe have your center of gravity in Apache Iceberg, and then you have these other formats that for specific use cases. And in the future, you might have other formats that come out for much even more fine-grained use cases, and I'll come back to that. So basically, this opens up a whole new conversation about table interop. Okay, how can I make these formats play together? Okay, because if I'm probably going to have to kind of mix and match a little bit, it would be nice to know that they can play together. So there's different ways you can kind of come to that story. So the simplest way, and probably the most effective way currently, is just to use tools that support multiple formats. This is one of this is like a tool like Dremio, but I mean other engines also support multiple formats. But with Dremio, you can read Delta Lake tables on your S3. You can read Apache Iceberg tables through several different catalogs, and write to Iceberg. But I could do a join. Okay, so if I could take that Delta Lake table that I wrote from Databricks and then take a Apache Iceberg table that I ingested via Flink into my S3, and then even a Snowflake table that's in my Snowflake because there's a Snowflake connector, and they can all play together nicely because you can then join them, create views on them, and do all that fun stuff because Dremio allows you to federate different data sources between databases, data lakes, and data warehouses. So that's one way they kind of have, just say, hey, I have these two data sets. Instead of me having to convert everything all the time, I can just use a tool that lets me work with both of them simultaneously. Then you have one house is creating a product called One Table. I mean, I think they are using it internally already. So I think like some customers are actually already taking advantage of this One Table technology. But as far as it being sort of like they've talked about like publishing a Git repo and getting people as a community working on it and making it separate from One House. So One House is the company, One Table is the project. But what One Table is that the idea would be that you could have two-way interops. So essentially, you could have a Hudi table and then be able to create Iceberg or Delta Lake or broadcast Delta Lake or Hudi metadata on that table and vice versa. Like have an Iceberg table broadcast Hudi or Delta whatnot, in all three directions. How basically there's a lot of different ways you can theoretically architect that. You could be creating that metadata on the fly, which I thought was the original design. So basically, you just have a Hudi table, and then on the fly you would project this sort of alternative metadata. But again, a lot of those implementation details haven't been released yet. But that's one of those projects that's kind of going in that direction. More recently was the announcement of Delta Lake's uniformat. So this is part of Delta Lake 3.0. Okay, and the overall goal is again to create three-way interoperability. So you'd be able to go from like Delta Lake to Iceberg and Iceberg to Hudi and Hudi to Delta Lake and Delta Lake to Hudi and so forth. Right now, the actual like what exists is you can go from Delta Lake to Iceberg. Okay, so all the other directions don't currently exist yet. And to use it, you do have to use the Unity catalog, which is part of the Databricks platform. Because essentially the way it works is that if you turn it on, every time you write to your Delta Lake table, it'll asynchronously, and that's a keyword, asynchronously, write a second set of metadata that's Iceberg metadata in the Unity catalog. And the Unity catalog uses the REST interface, which is like a standard REST catalog interface built into the Iceberg spec. So then it just allows certain Iceberg tools that work with Iceberg to be able to read those Iceberg tables from the Unity catalog. So that's how that works. So basically, if you're not using Unity catalog, then there's really no right now. Like that's the only catalog that metadata can get written to. So yeah, but it's a limit in that. And the other key thing to kind of keep in mind is that it's asynchronously writing the metadata. So if the Delta Lake table commit finishes, you have this like period of time between writing the second set of Iceberg metadata that a query could come in. So if a query comes into the Iceberg version of the table, and that metadata hasn't been written yet, they're going to query the old version of the table, even though the Delta Lake commit has already hit. Okay, so there is like this, it might be milliseconds, but there is theoretically like a moment of inconsistency between the two sets of metadata. And three, if there's a lot of transactions, it'll batch them. So basically, you might have 10 transactions or 10 commits to your Delta Lake table, but then they'll get batched as one commit to your Iceberg, the Iceberg version of the metadata. So again, it's a really early on in these stories. So probably a year from now, these are gonna all of these situations are gonna look very different. But if I were to speculate on what the inevitable like sort of like solution would be, like the thing that will sort of address this issue, I like the model of a company called Builder.io. So Builder.io, they create a CMS solution, for like building websites. And what they do is that they allow you to visually design your website, but then the actual like code can be in any of the front end web frameworks, so React, Vue, Svelte, so etc. So the so that would be really difficult to have to write code that just knows how to convert everything into every format. So what the approach they did is they created an intermediate format, a JSON format that captures all the abstract nature of the UI, that it's in a way that's easily transferable into any of these frameworks. So basically, by having that intermediate format, and then each framework just has to create one, instead of me having to create a transpiler for React to Vue, React to Svelte, React to, and then vice versa, you just create a transpiler from uh, React to this intermediate format, which was known as mitosis. So then what happens is that if you could translate to mitosis, then mitosis can translate to something else. So you go through two steps to get to to translate, um, and then that's how they're able to kind of support all these different formats. And then if another format wants to be added, all you'd have to do is just write one thing instead of writing six things. This is kind of, I think, how Google Translate works, where Google Translate doesn't go from like English to Spanish. It's kind of developed its own like immediate intermediate fake language that it's mapped all languages to, and essentially it'll go from English to the intermediate language and then from that to Spanish to make that translation step easier. So I do think something like that would probably make sense, like some sort of like intermediate, probably JSON based um, middleway format. It would have to be some sort of like company vendor agnostic project, some open source project. So that'll be the other thing, like because right now a lot of these are tied to like different vendors. But I do think like that's sort of where like that sort of like conversion interoperability will probably go. I think that's a good model for it. Um, but the question is like some of the different way the metadata works in some of them may not be as easily to translate, but I do think you could probably come up with something pretty close that'll let you move between. Esperanto, yeah, I spent all of last year learning Esperanto, and I've already forgotten all of it. Um, but hey, everybody, my name is Alex Merced. So this is the end of the presentation, and you guys can follow me on Twitter at amdata lakehouse. So on either that or on LinkedIn, I'm constantly posting about particularly data lake table formats, about Nessie and catalog versioning, data ops, data lake houses. These are sort of the topics I spend a lot of time talking about, and then I talk about them on these programs, which you can subscribe to on Spotify and iTunes. So do check those out, and what I'll do is I will open it up to questions. So let me open up the chat to see if I can see any questions that have come in, and let's see here. Okay, QA. Okay, yes. No, the intermediate language. Now, as far as again, how does the Google Translate thing? I can't. I don't know if it's Google Translate that was the one that did this, but I remember reading like an article where like the AI created the language itself. Like basically, it kept trying to learn how to translate better, and in the process of doing it, created the language itself for it to more easily translate between the different languages, which is, I don't know. I find that as like a sort of like a very like aha moment. And then when I saw that sort of similar approach applied at Builder.io, I found that really because I had to write an article on that particular technology a couple years ago, and I was like that was an aha moment. And then this seems like a good application of that approach, but again, there's definitely some extra challenges because unlike front end frameworks where they all kind of do the same exact thing, props, state, etc., not all of these track the same types of stats in the same way, um, with the same sort of approach to SQL. So there's definitely some there would be some deeper thought to have to go into how you would execute that. But yeah, if anyone has any questions, feel free to come off mic and ask or put it in the chat.
There must be
I
at
do
least a
have a
few questions.
question. Yeah, I do can you hear me?
Yep. Maybe.
Okay, yeah, I do have a question, but I kind of want to confirm my knowledge first because the question might not make sense if my understanding is not correct. Um, so Hudi, I'm kind of seeing it as a Kafka queue, and then it has like a pointer, whereas like all these like transactions or migrations that you can point to different things. Is that more or less a good?
Um, I would say, well, I mean, at least in use case purposes, it should be a little bit different than Kafka. You might take data from Kafka and ingest it into Hudi.
Mhm.
But I probably some aspects of its architecture probably that's kind of the case, as far as like creating a queue of transactions. But at the end of the day, like what you end up with when you have data in a Hudi format, there is actually files that actually will have listings of
Yeah,
files. So it's not just the process, but there's actually like um, actual files that are written that are specifically in a format that Hudi designed that'll track those files and the appropriate metadata for
yeah.
query
I was more
engines.
referring to like the layer of abstraction above like what happens at the file level and the actual like the bit level, but the actual transactions that get
Yeah,
caught.
I think that's probably not a bad way of thinking about it.
Okay. And then data lake, I think you mentioned too, is kind of like Git, where you have all these deltas and you have all these different commits, and you have. Is that a good way to think about it too? Uh, yeah,
Well, for Delta Lake, yes. So for
for
Delta,
delta lake, yeah.
yeah, for like they were they definitely chose a good name because a lot of people like they'll conflate the word data lake with Delta Lake and think they're one and the same. So it's it was very well chosen the name. But yes, no,
Yeah.
Delta Lake works a lot like commit, where basically you're capturing those changes. I mean, all three of them functionally do that, but Delta Lake's actual execution of it is very close to the way Git does it, where it's capturing additions and subtractions from the previous. While like Iceberg is just a completely separate snapshot and is a separate
Yeah.
list of what manifests make up the table at that point.
So my question is like, given that it seems like with Kafka you do have a way of like pointing different things, which you can establish a kind of version, and then Git you do have a way of versioning. You add tags or whatever to
Mhm.
like how do they not have the ability to do table versioning or catalog versioning if they are kind of like that, where you can take have that pointer or have a way to tag different commits or different deltas.
I think for Delta Lake they may have that feature built into the Databricks platform. Like I think they have like for your Databricks file system, there's versioning, and that's probably why they never implemented it for the actual format.
Okay.
So it's just kind of like, and then again, I don't want to seem like overly critical, but like basically like with the way Delta Lake is set up is like most of the people who make a lot of the decisions when it comes to Delta Lake is oftentimes like Databricks related people. So oftentimes, like for example, when they announced this whole uniformat feature, it wasn't like no one really knew it was coming. Like it was like basically they make this big announcement at the Databricks conference, and then people who are not Databricks people who are part of the Delta Lake community, they were surprised.
Mm.
So usually that's not quite how open source projects work. Because like for example, in Apache Iceberg, anytime they want to add anything, there first has to be a proposal, and then the proposal gets posted, and then everyone goes back and forth. Basically, you know very well that feature's coming like a year ahead of time because of the community process that takes to get there. But basically, some of those things like again, why isn't their version built into Delta Lake? You can see like okay, well, since it's one vendor that kind of steers the project, well, if they already have that feature built into their platform, they're less likely to think not that they not out of nefarious reasons. It's just like it's like more of like a blind spot thinking, oh well, we don't need it because we already got it here, but then people may want to use it in other places, and so you get the sort of difference, some level of sort of like of different way of evaluating how different features get implemented, um, with that sort of difference between sort of like a community based approach where everything is like very much deliberated by the community and everything's discussed in the public, where versus here where like a lot of things are like you kind of don't know where they're coming from. Like for example, like who sits on the technical steering committee of Delta Lake is not currently listed anywhere.
Okay. Cool. Thank you. I have another question, but I'll open it up, and if there's a law I
Oh,
can
go
ask
for
it.
it.
Uh, yeah, I guess there's no. Um, so you said that the ability to write schemas in this is kind of like schemaless and it's kind of open and you can change the schema as you go. Do you run into issues? Do you run into like worked with Elasticsearch or Mongo where you have all these different data things and as you change the schema, it kind of gets all over the place. So you have to like re-index. Like, do you run into issues with I guess an Iceberg or any of these with like
Um,
s-
there
with
are
like crazy
limitations.
schemas and then you have to like re-index whatever that means in this context?
Yeah, I mean, there are situations where if you make certain changes, it can be difficult to, like, more particularly if you try to delete fields. You may run into issues down the road, where when you try the bat when you basically try to do time traveling and basically now you have data that doesn't include that field at all,
Yeah.
and what but generally like best practices for all of that are generally outlined in the docs for like all three on like things that those sort of gotchas that they shouldn't be too hard to avoid, and they generally are built for like more common sort of patterns where probably most use cases it's gonna work out fine, and ideally schemas don't change. I mean, schemas change, but like it should work fine. Like I haven't seen it be as much of a problem in practice. Like there are edge cases where people run into, and generally people, if you go, like I'm part of like the Slack community for like all three formats, and you know people will hit those issues. But I would say where generally you see the most questions is just like the initial implementation, like basically moving their data over into these formats, getting sort of getting all those sort of common maintenance practices set in a way that just kind of they're on a good schedule. But once all that stuff's in place, generally it's pretty straightforward.
Okay. Cool. Thank you, and thank you for putting together this presentation.
No problem. I love to talk data. So anyone else got any questions? You got any questions? I got answers. Got a whole bag of answers here. Okay. Another moment. Okay. Well, with that, it's been a delightful time spending time with all of you. And again, follow me on Twitter, follow me on LinkedIn, and subscribe to these podcasts. And I look forward to seeing you all next time.